Hello everyone and welcome back to my channel. Today we are going to talk about small language models. We often hear about large language models, but what is this small language model? So what happened is in the internet we often find a lot of videos about large language model. So there are two spectrum. So there is one spectrum where we have how to run a large language model without knowing what is going inside, and then there is the very fine-grained part of how to code attention from scratch. So what I find is there is nothing in between that if I want to understand this whole language model shenanigan but in a more deeper level, but not as deep as that I have to code every one thing of it. So that's why I came up with this video where I'm going to walk you through training a small language model using pure PyTorch. Yeah, so that is one of the prerequisite to watch this video. Then you need to have some amount of knowledge for PyTorch and Python. So when you talk about large language model, there is definitely the transformers come into the play. This is the very popular architecture of transformer that you have seen multiple times by now. And in this video, I'm going to explain this architecture, but in a more simpler way and a more intuitive way by showing how the tensor flows, how the shape of the tensor changes, how they are multiplied, how they are added, what is positional encoding, all this. So just a teaser of this video can be summarized like this, that this thesis addresses the critical need. So this is a text that I want to pass through my language model, my small language model. So first I will tokenize it. So as there are 6 words in this particular sentence, I'll get 6 tokens, and they're also of course in the tensor form. So say 1 cross 6, 1 represents the batch size, but in this case I'm just have one sample, so batch size is 1 and 6 is the number of tokens. Then I pass that through my embedding layer, where for each token I get a dense embedding vector. We'll look through all of this throughout this video. This is just the summary that what we are going to cover. Then how we add the positional encoding, then the transformer architecture itself, this particular one, and then the output. In the output we have the vocabulary size. So suppose we have total 50,000 something words in our vocabulary, so our output will have that many number of neurons. So yeah, that's it. That's the whole small language architecture. And before diving in, let's see our target problem. What is our target problem? For this language model, our goal is to train it for next word prediction. For example, I have a corpus of text here, as you can see. This corpus of text is nothing but just the introduction of my own thesis, and I want to do the next word prediction. I want to create a next word prediction model, to be precise. So this is my language model, and what will be my input? My input will be some text from here. It's called extensive reviews of FDI, and my output will be algorithms. And after that, this algorithm will go and concatenate it with my input. So it will become like extensive review of FDI algorithm, and then my goal will be to predict the next word, which is in this case reveal. And like this I will frame my input output machine learning model. I hope that is clear for now. And after that, the first thing we need to look at is what is tokenizer. So as we know, the language model or any program for that matter do not understand languages. We have to encode it some numerical method. So for that, tokenizer comes into play. It's nothing but just a dictionary. So what this has, if you do this tokenizer is an object from Hugging Face, because in this YouTube series I'm going to use a lot of Hugging Face, and that is the Hugging Face transformer is arguably the largest and most used library for LLM, so that's why I'm going to stick to them. And for the tokenizer, if you do get vocabulary, then you can get some dictionary like this. So each of the character has a corresponding number assigned to it. And what you're basically doing is you're looking for that word or subword and their corresponding number. So yeah, for example, suppose you have the word called hello world, and with the tokenizer it will tokenize each and every character in the hello world to something like this. There is a hello, there is a comma, there is a world, there is exclamation mark, and everything got a tokenized format. And in this case, what I do is I use the GPT-2 tokenizer. If you do tokenizer.vocab size, then you can get how many total number of words or subwords are present in your vocabulary. And later on, suppose this is my input text and I want to tokenize it. So I just have to call this tokenizer, and inside I have to pass this text, and then it gives me the tokenized form. You see, there are six tokens present here. So here is the Jupyter notebook where I'll show a little bit how to execute this particular small language model. First, I'll import the necessary library. They're nothing special, mostly Torch, some NumPy, and from the transformer library, I'm importing the tokenizer. And after that, I initialized the GPT-2 tokenizer. If I run this, you see the vocabulary size is 50,257. And after that, let's first skip the dataset preparation part. We'll go into this later. Yeah, let's come here. So this is a chunk of text, and I want to convert them into tokenized form. For that, I just pass it through my tokenizer, and I mentioned that my return tensor should be in PyTorch format. So I get the output in PyTorch format, and this has a shape of 1x6 because just one sample, and there are 6 tokens. So I hope there is no doubt here. Now let's go to the next part. Next part is the embedding layer. So why we need this? Because these tokens, like for each token, we would like to create a representation. So the very simplest way would be to do a one hot encoding, but that will be 2 parts. For example, if we have 50,000 token, then each token will have to have a length of 50,000, and that's not practical, for example. So that's why we create a dense embedding layer. So what it does, it takes a particular token, and it basically a lookup table. So for each token, it gives you out a particular vector of certain size. So in this case, I decide it to be 64. So for example, if it passed the token 101, for that it has the corresponding embedding size of 64. So we'll get 1x64 vector, and we get the same for each of the element here in our sentence. And how do we do that? Using Torch's NN module, we create this embedding layer where the input is the vocabulary size and the embedding size. That's how we create the embedding, and if we pass the tokenized vector x, we get the embedded vector x embedding. So let's see that in the code. So here in the code, I specify the embedding size, which is 64. The vocabulary size I already have, which is like 50,000, and the embedding size. After that, I pass it through, and I get the shape of the embedding vector 1, 6. The 6 is for number of tokens, and 64 is the size of each embedding vector. Now move on to the next part, which is positional encoding. It's very important. And why we need it? Why we need this positional encoding? This is because the transformer architecture looks at one word at each time. So for example, this particular vector is treated individually. This vector is treated individually, so on and so forth for each and every word. There is only one part where they interact with each other, but still the model has no sense of which word came first. It doesn't know that the came first, then quick, then brown, then fox. If you give fox the brown quick, it should have the similar result. So that's why we need to give some information to the model that okay, this is the first word, this is the second, third, and fourth, so on and so forth. For that we need positional encoding. So how do we give this transformer that knowledge? Either we have one option that we can keep it learnable, that this positional encoding can be learned during the training so that the model learns on its own, or we can put it sinusoidal embedding. In this video, I'm not going to make it more complicated, rather I'm just going to keep it a learnable weight. But there is also another part that we can keep it sinusoidal embedding. And the main thing to understand is this is utilized to give the transformer model some sense of the position of each of the input. So here I specify my sequence length to be 10. And mind you that if I specify here sequence length to be 10, I cannot train it or infer a sequence length greater than 10, because this parameter cannot change their safe during training. They have to be kept constant. So I initialized some parameter with 0 values at the start, and they have the shape of 10 cross embedding size 64, which you saw here. And then when I'm adding that to my embedding vector that I got before, I'm only taking size up to embedding size. So for example, here I have 6 words, so I'll only add up to the 6th vector. That is one thing we have to keep in mind. If I fix my sequence length to be 10, I can take any sentence having number of words less than 10. For example, here I have 6 words, so I can use that, but I cannot use a sentence having 11 words. And finally comes the the transformer layer. And to implement this transformer layer, the PyTorch already has an implementation. From PyTorch, you can directly call this nn.transformer encoder layer or transformer decoder layer. They work basically the same. And you have to specify the D model, which is our embedding size, 64 in this case. So number of heads is the number of heads you want in your attention layer. Dimension feed forward is the dimension of this feed forward network. And batch first true is it expects the batch to be the first element. Right? For here we have 1 cross 6 cross 64, so 1 corresponds to the batch. That's it. And very clear and simple, we just pass the embedding with positional encoding to the model, and we get the contextual embedding from the transformer layer. So during the training, we have to use something called as a look ahead mask. So let's understand the significance of this look ahead mask and why we need it. This particular matrix you see here. This is basically the self attention, that how much attention each word in your sentence give to themselves and other word in that particular sentence. For example, we have a sentence called I am fine, and the first one is the start token. So our goal is to take this start token and predict the next word, which is I in this case. And then once we predict the next word, we concatenate with it to our input. So we'll have start I, and then we have to predict M. Then we have start I am, and we have to predict fine. So what is the main problem if we do not use any mask? For example, here, when we don't use any mask, the first word can get information from the future words, which is not ideal, because during the inference or the generation, we won't have information of the future word. So it can lead to performance degradation. It definitely leads to performance degradation. So for that, we mask the future words. So what we say the machine that when you are predicting the first word, just look at the first word. When you already have first two words, let's say start and I, then you can have you can have information from the first two words. When you already have the first 3 words predicted, then you can look the information for first 3 words, and so on and so forth. And this mask we have to pass through the transformer model. And how do we do that? And this is the mask we got. We got a triangular mask, basically this look ahead mask, and it has the sequence length cross sequence length. And next, when we pass the embedding vector with positional encoding, we also pass this mask, so that during the training, the information leakage doesn't happen between the first. While predicting the second word, it shouldn't know what came in the third word. So for example, here I have specified it to have 4 number of heads and hidden dimension to be 128. I initialized my transformer encoder layer, and if I print this out, I have just in this encoder layer, I have total 33,000 weights that needs to be optimized. And then I created this mask. I make this mask the same size of my how many number of words I have, and then I pass it along with my positional encoding with my position. Then I pass it along with my positional encoding, as you see here, and my output is still the same size, but they have more contextual understanding of the sentence. They know, they have seen what happens in the previous word, and they have gone through the attention phase. So now this embedding has more knowledge about the sentence. Now look at the final layer, which will do the prediction. And here in the main architecture of the transformer, you see this linear layer is the final layer. So what happens? This is your LLM, and you get in the end out of the transformer the contextual embedding, the embedding which have like rich knowledge of the entire sentence. Then you just pass it through a fully connected layer. That's it. And the output of the fully connected layer is all the words you have in your vocabulary. So according to the highest predicted word, you choose that word to be your next word. For example, here you pass this sentence, the capital of France is. In the output, you can choose only one word, but for that you usually choose the word with the highest probability, but there are other words also with having less probability. And for this case, we'll choose Paris, but there is also chance that someone can change dense, diverse, something like that. And how does this work in the PyTorch environment? You put just a linear layer, plain and simple. The embedding size, which is in this case 64, and the vocabulary size is 50,000. So it goes from 64 to 50,000. And among those 50,000, whichever has the highest probability, we choose that. As simple as that. And that gives us the logit. So after we create the final layer, we just pass the contextual embedding and we get the logits. And here is how you implement this. You just pass it through the model, and the output is still 6 words, and you got 50,000 output, and you choose the one with the max. So among 6 words, we do not care about the first 5, by the way. We just care about the last word, because we need to predict the next word, right? So we don't care about what it predicted before. We just care about the last word, which one it predicted. So for the last word, we see which among this has the highest, and that word we consider. Now let's see how we calculate the loss and to optimize the weight for that. So first we have a text, some random text that we take from our corpus, that is our X, let's say. We pass it through the tokenizer. Here we have 10 words, so we get a tokenized vector of 1 cross 10. Then we pass it through our language model, and we get the logits, which is 1 cross 10 cross 50,257. Alright, so this is my output from the language model. By the way, in tokenizer there are no weights, nothing gets optimized in the tokenizer. Then my output will be just one letter shifted towards the right. For example, this is my input. This thesis addresses the critical need for effective fault detection. My output will be this will be removed, and there will be a new word added towards here. So it will be thesis addresses the critical need for effective fault detection, and is the word basically I want to predict. And for the target also, I will do a tokenization step. Now my target will have 1 cross 10, and then I'll do the loss function, which will be the simple categorical cross entropy loss. And with that loss, I'll just optimize my weights inside the language model. So let's see an example of how to calculate a simple loss. What I did is I put first what I have to do is I have to put all the corpus of text there, and then I'll tokenize the entire corpus of text. So in the tokenized text, I have just the tokenized version of all my entire corpus of text. Then I specify my sequence length. In this case, I specify it to be 10. It can be anything depending, which is also known as the context length, by the way. Right now we talk about million context length, which is the ChatGPT 4o has. This is what they are talking about: sequence length or context length. That how much of the input we can give to the chat. In this case, the language model. You understand? So what will be my X? My X will be all the row, all the rows. In this case, it's just the batch size, which is 1, and then it goes from 0 to sequence length up to the 10th element, and the y is will go from first element to sequence length plus 1. That means just one shift. So you see, this is my input and this is my output, which is, you see this thing is here and so on. They just shifted towards the left. So yeah, this is my x, this is my y. Now we'll see how to calculate the loss. So to calculate the loss, I need to get the logits. First, I'll pass the tokenized x into the embedding layer. Then I'll add the positional encoding. Then I'll create a mask, the look ahead mask. I'll pass it through my transformer layer. Here mask is also another input. Then I'll pass it through my final fully connected layer. I'll get my logits, and this is the loss function I'm going to use, which is categorically cross entropy loss function. And if we do the loss function, we get the loss. Right now the loss is 10.99 or something like that. The loss between the logits of x and the y. Alright, now that we understand that, now let's create the model, because here we understood how this transformer model works each layer at a time. Now put all of them together to create our small language model. Here I created the transformer language model, and in there I initialized the embedding layer, the positional encoding, the encoder layer, and the fully connected layer. And then I just did the same. I just passed them through. And in the forward method, what I do is I pass the x through the embedding layer. I add the positional encoding to it. Then I pass it through the encoder layer, which is the transformer layer. Then the fully connected layer. Very simple. I have also option of specifying the mask. This mask I only need to specify during the training. I don't need to specify during the inference. Alright. Then I specify my number of epochs, which is 20, and the learning rate is 0.001. You can try around. It's nothing specific. I create my optimizer, and I want to optimize the weights of this model. Okay, the dataset is not defined. Alright, so I forgot to tell about the dataset. How do we create the dataset? It's very straightforward. This dataset is the PyTorch dataset, where you just have to specify the input and output, how you get one input and one output, and it does everything for you automatically for each index. So it's the same that we saw before, that from index to index plus sequence length, then index plus 1 to sequence length plus 1. That's it. That's all it has. I have already made a video about PyTorch dataset and data loader. If you haven't watched, I'll put a link to that in the description. Then from this dataset, I created a data loader as well. So what does the data loader does is it takes a batch of input from this dataset and feeds it to my during the training. With that out of the way, now let's start the training. For starting the training is very simple. We go XY in data loader. We create the mask, the triangular mask that we talk about, look ahead mask. We pass it through the model. We get the output. We calculate the loss. We back propagate the loss. Then we optimize the weights, and that's it. Now you just have to run it. See, we see the loss decreasing. That means our model is learning. See, we went from 10 to 0.29, which is definitely good. So right now, as our model has trained on our corpus of data, we should give it only one word and it can just generate the next word, next word, next word, and fill up the entire sentence. That's what it should happen. Let's see if it happens or not. And to do that, we'll first pass a small text from the corpus it is trained on, a key player in mitigating the greenhouse effect. I pass it. And yeah, see, the generated text is a key player in mitigating greenhouse effect. To tackle this challenge, this thesis introduces a hybrid strategy for FDI, extensive reviews of FDI algorithm and everything, which is very coherent. Like it doesn't seem like AI generated. It seems like exactly what I've written, and that's what we did. We basically overfitted the model on a small part of data and is fairly able to replicate this. And this what goes to train a big language model as well. This is the first part, which is the self-supervised training, kind of like next word prediction. So let's see how this inference work. I'll give you the overall idea. So we give it a random piece of text to start with, then we convert it into tokens, of course. We pass it to our large language model. As there are 10 words here, we get the logics for 10 words, but we need to just care about the last one. And in this case, we do not need the look ahead mask because we do not have information from the future word. So here we get the logic, which is of the shape of 1 cross 10 cross 50,000. But we just need to care about the last word, the prediction of the last word. If we do argmax here, we get the maximum prediction for each of the word here. And if we plot, if I print them out, it looks something like this. So it predicted that thesis introduces the F need for effective fault detection, and but what I care about is just the last word, because this one then gets added to my input context, and then this entire part is passed into the language model. But you'll say that because after a certain length, this will way past, because it keeps on growing. Right now it's 10 word, but if I keep on adding to it, it will keep on growing as well. So when it grows like beyond 10, then I just take the recent 10 words, pass it to my language model and do the prediction. My context length cannot change because it's maximum 10 words. Even though in my input I have more words, I cannot pass it to my model right now. And yeah, if I go a little bit and explain here. So this is the word I started with. This is the text I started with. I tokenize them, and I pass this input sequence to my model. I get the output. In the output, I just take care of the last word. What is the maximum value for the last word, the prediction of the last word? That will be my next token. And I keep on like whatever is my next token, I pass that to the generated corpus of text I have. It keeps on appending to it. So yeah, what I did is I just printed step by step. So first my input was this much, and the output was 2. Then this was my input, like up to 10 words, and then the output was this. Then my input was this much, and the output was this, so on and so forth. Right, so you see how the output keeps on increasing. Okay, so that was it about this video. Here we understood how a language model works, but not to the extent that we have to code everything, but not to a very superficial extent. We understood many things. Yeah, that was it about this video. If you have any feedback or you did not able to understand some part of it, don't hesitate to leave it in the comments. And if you want more videos on large language model explaining like this, do let me know. Until then, stay curious.